Welcome! We saw in electric fields that if we have an infinite plate, that it gives us an electric field of sigma over 2 epsilon naught. We use positive, negative, and which side of the plates they are in to find out the direction. If we place this positive plate a distance d away from a negative plate, both of them being infinite plates, we get what we call a parallel plate capacitor. So let's do a little bit of investigation of this. So we are going to say that they have the same charge and the same area. And since our sigma, our charge density, is equal to charge over area, we can say this is Q over 2A epsilon naught. So what we can look at is we can look at three different regions. We can look off to the left of both plates, off to the right of both plates, and we can look inside both plates. So off to the left of both plates, for my positive plate is always going to be pushing the electric field away. So the left plate is going to have then the electric field from the positive plate looking in this direction. Inside, again, going to be pushed away, so off to this direction. So I'm going to have E plus in this way. And over on the right side, I will have still again pushing away, and so I have E plus. Under this assumption of the infinite plate, right, we don't have any distance to worry about. These are constant fields. Then if we look at our negative plate is going to want to be pulling everything in. So going from the right to the left, from the right it's going to be pulled in. So we are going to have this electric field minus. On the inside, it's going to be pulled in, so we're going to have this electric field minus. And from the left side, going to be trying to pull it in, so this electric field minus. So if they have the same charge in the same area, they then have the same field in all regions of space. So looking at the left side, I have that E minus is pointing in the positive direction. E plus is pointing in the negative direction, so E minus minus E plus. And since they're of the same magnitude, I would get 0. For the right side, I have E plus is now moving in the positive direction, and E minus is in the negative direction, and so I'd get 0. On the inside, I get that they both are going in the positive direction, so I get E plus plus E minus is 2 times the magnitude of this. So the electric field inside is twice one of these plates, or Q over A epsilon naught. This is all great, but this is still electric fields. Electric fields, right, and electric potential, very, very nice. What if we were to do a path from here to here to find the electric potential? So my electric potential delta V is equal to the negative integral of E dot ds. Any amount that I start on the left, the electric field is 0. So 0 dot ds is going to give me 0. For the inside, I've got this electric field of Q over A epsilon naught, and right, Z hat dotted with ds. And right, negative because we have a negative here, and so negative because we have a negative here. And on the right side, my electric field is 0, so then I have just this 0 ds. This is just to show, right, we can start any amount to the left, any amount to the right of these plates, and no matter what, as we're going in them, the electric field to the left, to the right is 0. So really, we just want what's here. And what's nice is, of course, is that our electric field is constant inside the plates, so we can go even easier and say that it's, pull it out, Q over A epsilon naught integral of ds. So as we go between the plates, we are going from this part of the plate to this part of the plate, or a distance d, and so we get the delta V from a capacitor is negative Q d over A epsilon naught. This is totally reasonable, totally great, but what's interesting is that as I print a capacitor, as I make a capacitor in a factory or anything like that, I can't really change the spacing between the plates. I can't really change the area of the plates. But after it's rolled off the factory, I can put any amount of charge on either side of the plates. So the only thing that I'm really able to change in my circuit in a general sense is Q. And I don't really care what the D's, the A's, or anything like that. I just care what the total sum is. And in fact, instead of D over A epsilon naught, we're going to look at A epsilon naught over D. This is what we care about for our parallel plate capacitor. We are going to call this the capacitance C of a parallel plate capacitor. So every time we see A epsilon naught over D, we can replace it with C. And so then we get that the delta V of our capacitor is negative Q over C, just to make things quite a bit easier for ourselves. But in a general sense, right, we can solve for this C. So generally, for any shape, the capacitance C is then the magnitude of the charge on both sides over the change in voltage. So we will see, right, cylindrical capacitors or things like that, much more common in the real world than parallel plate capacitors. And this is how we'd calculate the capacitance for that.